Hello everyone. We have been discussing the effect of different factors on the fate of addition reaction to alpha beta unsaturated carbonyl compounds. Previously, we have discussed the effect of reaction conditions and the structure of the molecule. The nature of the nucleophile can also affect the overall fate of the reaction, whether it will follow direct addition or conjugate addition. So in this video lecture, we will talk about the effect of the nature of the nucleophile on the fate of the addition reactions on alpha beta unsaturated molecules. So nucleophiles can be of two types. Nucleophiles may be hard or soft. Hard nucleophiles preferably react with hard electrophiles, and soft nucleophiles react with soft electrophiles. Now, this is a general trend. You may have heard about soft and hard acid bases, in which hard bases prefer reaction with hard acids and soft bases react with soft bases. And the same is true for the combination of electrophiles and nucleophiles. So we will follow the general trend, that is hard nucleophile reacting with hard electrophiles and soft nucleophiles reacting with soft electrophiles. Now we have the nucleophiles that will be added to the reaction mixture, and some of them may be hard and some of them may be soft. But before going into this, let me just tell you briefly what a hard or soft electrophile or nucleophile mean. So from the soft and hard acid base concept, you already know that hard species have a higher charge density while soft species have a lower charge density. Moreover, the polarizability of soft nucleophiles or bases is also greater than hard nucleophiles or bases. So based on this criteria, we can classify these nucleophiles as hard and soft. So you see here the halogens, that is fluoride ion, chloride ion, water, hydroxyl ions, alcohols, ammonia, and alkoxide ions. These are regarded as hard nucleophiles because of higher charge density and lower polarizability. Similarly, on the right hand side, you can see the iodide ion with a larger size and the same charge as that of the fluoride ion, but because the charge can easily be accommodated because of the larger size of the iodide, so the charge density is lower and the polarizability is also higher. And then we have the sulfide ion, the thiols, the sulfide ion, alkenes, aromatic species. They all act as soft nucleophiles. Then there are some nucleophiles which we call the borderline nucleophiles. So you have cyanides, this primary amine, bromide ion, etc., which are at the borderline of hard and soft nucleophiles, meaning they can undergo both direct addition or conjugate addition, provided the reaction conditions favor one of the two types of reactions or mechanisms. Now, these hard and soft nucleophiles will react with an electrophile. The electrophile in these reactions is of course the alpha beta unsaturated system, and you already know that when we are talking about this alpha beta unsaturated molecule, we have two centers available for attack. So you have the carbonyl carbon here, which is of course electrophilic in nature, and then we have a double bond between alpha and beta carbon. And because of resonance, you know that this beta carbon is slightly more electron deficient as compared to the alpha carbon. So attack can occur both at the carbonyl carbon as well as the beta carbon. Now we have to analyze both of them, the carbonyl carbon as well as the beta carbon, whether they are soft electrophiles or hard electrophiles. You know, here at the carbonyl carbon, the carbon itself is attached to a highly electronegative oxygen. So because of inductive effect, the bond is highly polarized, and so you know that the charge density is higher here because it is more electrophilic as compared to the beta carbon. So we regard, or we take this carbonyl carbon as a hard electrophile, while the beta carbon, of course, it is electron deficient also, but slightly lesser, to a lesser extent than the carbonyl carbon. So this would be our soft electrophile. So among all of these nucleophiles classified as hard and soft, the hard nucleophiles will preferably attack the carbonyl carbon, while the soft nucleophiles will preferably attack the beta carbon. These borderline nucleophiles, the reaction of them will depend upon the reaction conditions and, of course, the structure of the substrate. So we can have this Grignard reagent as a nucleophile. You know, it's an organometallic compound, and because of this carbon metal bond, the carbon act as a nucleophile. So normally a Grignard reagent or the alkyl magnesium halide, the alkyl group acts as a hard nucleophile. And we have already seen that inside this alpha beta unsaturated system, this carbonyl carbon is a hard electrophile. So this alkyl group will preferably attack the carbonyl carbon, shifting this pi bond towards oxygen, and in the second step, an acidic workup will lead to the formation of this tertiary alcohol. You see, the double bond of the alpha beta unsaturated system remains unchanged, untouched, and the reaction happens only at the carbonyl carbon. It is because of the fact that the nucleophile that we are using is a hard nucleophile, and it will attack the hard electrophilic carbonyl carbon. But if we change the organometallic compound, here we have dialkyl lithium cuprate. In place of magnesium, now we have copper, and copper, you know, because of larger size and higher polarizability, this alkyl group here acts as a nucleophile, of course, but a softer nucleophile. Now, this softer nucleophile will obviously attack the beta carbon rather than this carbonyl carbon. So, attack at the beta carbon will shift the electron density in this way, leading to the formation of an enolate anion, which is trapped by acidic workup, and that enol is then converted into ketone due to tautomerism. So you see that this alkyl group gets attached at the beta position, and the carbonyl is untouched in this case. So just by the look of the nucleophilic species or the nature of the nucleophile, you can see that the hard nucleophile attacks the carbonyl carbon, while a soft nucleophile attacks the beta position. Here we have the reaction in which you can prepare this dialkyl lithium cuprate. Of course, you can start with an alkyl lithium and react it with copper bromide in diethyl ether at minus 78 degrees centigrade. You will get this dialkyl lithium cuprate along with the release of lithium bromide. Here we have another example, and you see now that this carbon is substituted, the beta carbon is substituted. If you react it with an alkyl magnesium bromide, as you saw in the previous example, this alkyl group will preferably attack the carbonyl carbon, leading to the formation of this tertiary alcohol. But if you look at the products, you see a spread of two different products. So as you know from the previous example that this alkyl magnesium bromide will attack the carbonyl carbon because it's a hard nucleophile. So it attacks here, leading to the formation of this tertiary alcohol. But if you look at the products, you have 43% of the tertiary alcohol and 48% of another product here. Now, how does this product forms? You see, when alcohol is formed here and this double bond remains untouched, we can have the removal of water from this molecule, forming another double bond here. And these two double bonds are in conjugation, so that leads to a more stable product. If you look at the spread of the products, this this product is formed in 48% quantity and this is in 43%. So it goes for direct addition, but then it leads to the removal of water, forming this conjugated diene system, which is of course more stable, and that is why the percentage is higher. But if we add a small amount of copper chloride to this alkyl magnesium bromide, then of course the polarizability changes, the nature of the nucleophile changes, and then this alkyl group will preferably attack this beta carbon. So if it attacks the beta carbon, the alkyl group gets attached here. You see this beta carbon now has two alkyl groups attached to it. This carbonyl group remains unchanged, but some of it may attack the carbonyl carbon as well, like in the first example here, and then after dehydration it may lead to the formation of this product here, like you can see here. But if you look at the percentage, this product or the conjugate addition product is formed in 83% and this is only 7%. So this is the product of the direct addition, but because you can see from the nature of the nucleophile that it will preferably attack the beta position, this conjugate addition product dominates while the direct addition product is only formed in 7%. So from the nature of the nucleophile, you can tell in which direction the reaction is going to proceed, whether it will lead to direct addition product or a conjugate addition product. So a hard nucleophile will preferably lead to the formation of a direct addition product, while a soft nucleophile will lead to the formation of a conjugate addition product. So this is it for today. Thank you so much. See you next time with another topic. Thank you.